Making a project work is an achievement. But does that mean we understand the engineering behind it? Our young engineer discovered important mistakes in his own journey.
When I first started building engineering projects, my main goal was simple. I wanted to make them work. And when something finally worked, I felt that I was making real progress as an engineer. Looking back now, I realized that I made 5 important mistakes. At the time, I didn't even recognize them as mistakes. I thought that because I could make something work, I understood it. But later, when I started facing more difficult engineering problems, I began to see the difference. Making something work is one achievement. Understanding why it works is another. Let me share the 5 mistakes I now recognize from my own learning journey. Like many engineering students, I started with curiosity. I would see an interesting robot, electronic system, or engineering project and think, I want to build something like that. Then I would search YouTube, ask questions online, find tutorials, download code, and identify the components I needed. I would buy the components, connect everything together, modify the software, experiment with the system, and eventually make it work. And I still believe that was valuable. Building gave me motivation. It gave me confidence. It gave me practical experience that I could never have gained simply by reading a book. So the mistake was not that I started building before I knew all the theory. The problem was what I sometimes did after the project worked. Instead of treating that success as the beginning of deeper learning, I sometimes treated it as the end. At that stage, I became quite good at making things work. I could connect components. I could modify software. I could adjust parameters. I could follow tutorials and solve many practical problems. And eventually, I could usually get the result I wanted. But I later realized that there was an important difference between saying, I can make it work, and saying, I understand why it works. Could I explain the behavior? Could I calculate what was required? Could I predict what would happen if the conditions changed? Could I justify why I selected a particular motor, sensor, mechanism, or controller? And if the requirements changed, could I redesign the system myself? Those questions made me realize that a working project and engineering understanding are not the same thing. And that leads to the first mistake I made. The first mistake I now recognize was false confidence. When my project worked, I naturally felt that I understood it. But if someone had asked me deeper engineering questions, I might not have been able to answer them. How much torque does this motor actually need? Why did I choose this gear ratio? How much current will the motor draw? What loads are acting on the structure? How accurate is the system? How close are the components to their limits? And what happens if I double the payload or increase the speed? The project could work even when I could not answer these questions. Perhaps I had selected a motor much larger than necessary. Perhaps a component was operating close to its limit. Perhaps the system worked only because the operating conditions were easy. I eventually learned an important lesson. A successful demonstration proves that something works under those conditions. It does not automatically prove that I understand why it works. My confidence had grown faster than my engineering understanding. My second mistake was allowing trial and error to become my normal way of solving engineering problems. If something didn't work, I changed a parameter and tried again. If that didn't work, I changed something else. Maybe I changed the code. Maybe I replaced a component. Maybe I changed another parameter. Eventually, something worked. At the time, I thought this was engineering problem solving. Later, I understood that experimentation itself was not the problem. Engineers experiment all the time. The important question is, why am I making this particular change? What do I predict will happen? Can I explain the result? A good experiment should test an idea, a calculation, a model, or a prediction. So I began trying to change my approach. Instead of change, try, fail, change again, I wanted to understand, calculate, predict, test, and then learn from the result. I still experiment, but now I understand that experiments should help test my understanding, not replace it. My third mistake was following online solutions without questioning the engineering decisions behind them. A tutorial might tell me, use this motor, use this gearbox, use this sensor, set this parameter, install this library, use this code. I would follow the instructions, and quite often the project worked. But I was seeing only the final choices. I was not necessarily learning why those choices had been made. Why this motor? Why this gear ratio? Why this sensor? Why this sampling rate? Why this control method? Why these controller gains? Someone had already made those engineering decisions for me. They may have considered requirements, calculations, constraints, trade-offs, testing, and experience before arriving at that solution. I was reproducing the result without necessarily understanding that reasoning. So I learned to add one very important question whenever I follow an existing solution. Not only what did they use, but why did they choose it? Because one day, my requirements would be different. My fourth mistake was perhaps the most serious. Because I could already make things work, I sometimes began to feel that some of the theory was not really necessary. My robot was moving. My electronics were working. My software was running. So why did I need to go deeply into mechanics, dynamics, electronics, mathematics, or control theory? After all, I had already built something that worked. Later, I began to understand why this way of thinking could limit me. The theory becomes essential when the problem changes. What happens when I need the robot to move twice as fast? What happens when the payload increases? What causes the vibration that suddenly appears? What determines the positioning accuracy? What happens when I need to design something for which there is no tutorial? Now I need to calculate. I need to predict. I need to understand the physical behavior. And I need to make engineering decisions myself. I eventually realized that theory was not separate from the practical work. Theory was what allowed me to go beyond what I had already managed to build. My fifth mistake was confusing reproducing an existing solution with designing a new one. If I found a good tutorial, I could often build the project. I could obtain the recommended components, follow the instructions, modify the software, troubleshoot the problems, and eventually make it work. That gave me useful practical skills. But then I began asking myself a harder question. What happens when there is no tutorial? Suppose the robot must carry twice the payload. Suppose it must move faster. Suppose it needs much higher accuracy. Suppose there are new restrictions on size, cost, power, temperature, or safety. Now I cannot simply reproduce somebody else's solution. I have to understand the requirements. I have to perform calculations. I have to compare alternatives. I have to predict behavior and make design decisions. That was when I began to understand the difference between building an existing solution and engineering a new one. The real test was no longer, can I build this? It became, can I design something when there is nothing to copy? After recognizing these mistakes, I did not conclude that I should stop building. In fact, I came to the opposite conclusion. I should keep building. I should keep experimenting. I should keep making things and gaining practical experience. But I needed to change what happened after I made something work. I began to see that I needed two things to develop together: practical ability, building, testing, troubleshooting, experimenting, and making things work, and engineering understanding, explaining, calculating, predicting, selecting, and designing. I don't think one should replace the other. Theory without practical experience can become disconnected from the real system. But practical experience without deeper understanding can limit how far I can progress. So the lesson I learned was not, stop building until you know all the theory. It was, keep building, but use what you build to take yourself deeper into engineering. So I began trying to change the way I learned from projects. Making the project work was no longer the final step. It became the starting point for another learning cycle. I would build something, then observe what it actually did, measure its performance, look at its limitations, and most importantly, start asking questions. Why is the motor getting hot? Why does the robot vibrate at this speed? Why does the positioning error increase when the payload changes? Why did changing this parameter improve one behavior but make another worse? Those questions told me what I needed to learn next. Then I could study the relevant theory, do the calculations, create a model, make a prediction, and return to the project with a better design. Then test it again. If the result agreed with my prediction, my understanding became stronger. If it didn't, I had another question to investigate. I began to realize that the question why is the bridge between building something and learning engineering from it. I also began using a different test to decide whether I really understood something. I no longer asked only, does it work? I started asking, can I explain why it works? Can I calculate what is happening? Can I predict how it will behave? Can I justify why I selected these components? Do I understand its limitations? And perhaps the most important question, if the requirements change, can I redesign it myself? These questions changed the way I looked at my projects. A working project was still something to be proud of, but now I wanted more than a successful demonstration. I wanted to understand the system well enough to explain it, predict it, improve it, and eventually design the next version myself. For me, that became a much better test of engineering understanding.